Let's start talking about telescopes. There are two kinds: refractors that use lenses and then reflectors that use mirrors. This lesson is talking about those refractors. Now, Galileo Galilei is one of the most important physicists and astronomers of all times. Galileo first used a telescope to look up into space in 1609. Galileo did not invent the telescope. It was actually invented in the Netherlands, but Galileo read about it, thought, oh, what a wonderful invention, built one himself. That meant he had to grind all of his own lenses out of pure glass and put one together. And as far as we know, Galileo was the first person to actually look up into the stars and record his observations. Scientifically, not just because it's fun. This picture on the right is a picture of Galileo's actual telescope. This is located in a museum in Italy. The fancy gold-plated stand was not there when Galileo was first looking through the telescope. And you'll see that it is a very humble, not very elegant looking affair. But that simple long tube allowed Galileo to make some pretty amazing astronomical discoveries, which we will talk about in Chapter 5. Now, how is a Galileo telescope put together, or refracting telescopes put together? There are two basic types of refracting telescope. One is called a Kepler telescope. Johannes Kepler was a contemporary of Galileo's, meaning he lived approximately at the same time. And Kepler invented a telescope that involved two converging or convex lenses. So the light from a distant star would come in, go through the first lens, form a real image here, and then the observer would look through the eyepiece lens and see a virtual image here. Now, the virtual image, because the observer is looking through the lenses to see it, would be much, 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 much larger due to the magnifying power of the individual lenses. The challenge with the Kepler telescope is this. Can you see the problem? Yeah, the thing that you're seeing is upside down. Now, most of the time, if you are looking at a star out in space, you don't really care, but it does get to be a little wacky when you're trying to figure out where things are. Galileo made a better telescope, and Galileo's telescope contains one converging or convex lens and then one concave or diverging lens. And here's how this works. If there is a star out here, the light from that star would come through the first lens and it would produce a image in this concave lens that the observer would then have to look through to see. It's a lot more complicated optics, but the beautiful thing about the Galileo telescope is that now your image is right side up, and you're not trying to look at things upside down, which is, like I mentioned, kind of awkward. There's a problem with all refracting telescopes or telescopes made out of lenses. They suffer from a defect called chromatic aberration. Chromatic aberration means that the image is going to appear as if it's ringed in color. And here's why this occurs. Remember that white light is actually made of all colors of the rainbow. Well, each individual color of light is bent or refracted a slightly different amount as it goes through the lens. What this means is, instead of having one focus for everything, the short violet light focuses in one spot, the long red light focuses in another spot, and everything in between. This leads to things being a little bit blurry. Here are a few pictures of what chromatic aberration actually looks like. If you pass light through a thick lens, you are going to see the object, and obviously this is a weather vane, ringed in color. So this weather vane of a horse, you see red colors and oranges up here, you see blues and cyans and magentas down there. The object is actually broken down into various color. This picture of penguins that contains chromatic aberration, you'll see that the head of the penguin here looks like it's blue and pink, and the side of his fin, I'm not quite sure, I'm not a biologist, but this right here looks blue, and this back of this penguin also looks blue. So it means the images are not crisp. Here's an image of a building with chromatic aberration and without. Without, it's much crisper. Without, with, it has a tendency to be just a little blurry. In the world of astronomy, if you are trying to look at a moon, planet, star, the challenge is they are going to be also rimmed with chromatic aberration. So this, of course, is the moon observed through a simple, cheap telescope. I've had numerous students through the years who have simple telescopes bring me pictures of what they've seen by looking through those telescopes. And this is the kind of image that they get because it takes a pretty expensive optics to not get chromatic aberration. Okay, smart people, what's that a picture of? Jupiter. Yeah, that's Jupiter. Again, through a relatively simple, cheap telescope, and chromatic aberration has made it ringed in color. Chromos is the old Latin word for color. So that's what this ringed in color chromatic aberration. How do you correct for it? Well, when you buy a fancy telescope, it contains not just a couple lenses, it usually contains many, many, many lenses. And the people who do optics for a living will combine converging and diverging lenses to pull all of the colors together at one point or reduce the size of that blurry zone. And that is what makes good telescopes infinitely more expensive. Here's two images, of course, of a cheetah, chromatic aberration, and without. The world's largest refracting telescope that contains a big honkin' lens to do all of the work is, amazingly or not, located in the state of Wisconsin. It's down north of Chicago, Illinois. This telescope is actually owned and operated by the University of Chicago. And this telescope was built in 1895. That is very, very old. That's over 120 years ago that this telescope happens to have been built. That might give you a hint about how good refracting telescopes are if we haven't built one bigger in the last 125 years. And that's because of a whole host of problems, one of which is the fact that glass is not really, really strong. If you go to an old house, you might notice the windows in an old house look a little ripply because the glass over time will be sagged downward because of gravity. Well, if you have a huge lens on the end of this telescope, the challenge is over time that lens is going to get a little fat bottomed due to gravity, and it will go out of alignment and out of shape. That's one of the challenges with refracting telescopes. This is a more modern picture of that refractor at Yerkes Observatory at the University of Chicago. Actually, it's not at the University of Chicago, it's up in Williams Bay, Wisconsin. So refracting telescopes. This is the kind that Captain Jack Sparrow uses on the Black Pearl. You look through the end, it's got lenses here, it's got lenses there, and a long tube. They are simple, they're cheap, they are limited by chromatic aberration, but if you want one for home use, you could get one for $100. Under 200, you can get a decent one. All right, next lesson we're going to come back. We'll start talking about reflectors.